Welcome to Unacademy Ascent YouTube channel. This is K Umamaheswara Rao. Today I will be discussing MSQs and numerical answer type questions on complex variable. MSQs and numerical answer type questions on complex variable. First problem. At z equal to 0, the function f of z equal to exponential z by e power z by 1 minus cos z has a removable singularity or pole or essential singularity, and Lorentz series around z equal to 0 has infinitely many positive and negative powers of z. E power, our function is e power z by 1 minus cos z. E power z by 1 minus cos z. Now, this can be written as e power z by 1 minus cos z, 1 minus of 1 minus z square by 2 factorial plus z power 4 by 4 factorial and so on. That can be written as e power z by 1 minus 1 plus z square by 2 factorial minus z power 4 by 4 factorial plus and so on. 1 and minus 1 cancel. Now this can be written as e power z by z square by 2 factorial minus z power 4 by 4 factorial and so on. You can take z common. Z by taking z square common in denominator, 1 by 2 factorial z square by 4 factorial and so on. Now e power z by z square means 1 by z, na? 1 by z of 1 by 2 factorial minus z square by 4 factorial and so on. This is equivalent to e power 1 by z. Now, e power 1 by z can be written as 1 plus 1 by z by 1 factorial 1 by z square by 2 factorial 1 by 3 factorial into z cube and so on. So here you have infinite number of negative powers of z. Infinite number of negative powers of z. If you have infinite number of negative powers of z, then z equal to 0 is essential singular point. That's why in this problem z equal to 0 is essential singular point. So third option is true. Not only that, when you look at the series, you have infinite number of negative powers of z. So it is a Lorentz series expansion around 0 has infinitely many positive and negative powers of z. This is also true. So third option and fourth option are true. MSQ, both C and D are found correct in this problem. Good evening, Vishwaranjan. Thank you. Next column. Let the function f from complex system to complex C to C, complex variable to complex plane be an analytic function for z equal to x plus iy, u comma v belongs to r square to r, such that u of xy is real f of z, if v of xy is imaginary f of z, then which of the following are correct? Now here, given that z is x plus iy, given that z is x plus iy, function of z is u plus iv. Now u is a real part of z, real part of function of z, v is imaginary part of function of z. Then which of the following statements are true? We have to identify. Now, whenever the given function is analytic function, then compulsory, whenever f of z is analytic, given that f of z is analytic, therefore if the given function f of z equal to u plus iv is analytic, definitely the real part of f of z u and imaginary part of f of z v both satisfies two-dimensional heat equation, that is also known as Laplace equation. Therefore we can write del square u by del x square plus del square u by del y square equal to 0, del square v by del x square plus del square v by del y square equal to 0. Both real part of f of z u and imaginary part of f of z v both are harmonic. That's why both u and v satisfies Laplace equation. That's why I have written del square u by del x square plus del square u by del y square equal to 0. Del square v by del x square plus del square v by del y square equal to 0. These two equations are nothing but our first option and second option. This is true, this is also true. Now we have to verify third option and fourth option. Now, whenever the given function is analytic, definitely Cauchy-Riemann equations are satisfied. Therefore, ux equal to vy, uy equal to minus vx are satisfied. Now we have to examine third option, because this is option A, this is option B, both are true. Now come to option C, del square u by del x del y minus del square u by del y del x, del square u by del y del x. Actually del square u by del x del y minus del square u by del y del x equal to 0. The reason is both are equal. That's why directly you can write, no problem. We can use CR equations. Del by del x of del square u by del x del y is del by del x of del u by del y minus del by del y of del u by del x. Del u by del y, uy equal to minus vx, uy equal to minus vx, uy equal to minus vx minus del by del y of ux equal to vy. Therefore this can be written as minus del square v by del x square minus del square v by del y square. If you take minus common, del square v by del x square plus del square v by del y square. Anyhow, del square v by del x square plus del square v by del y square is 0. That's why minus of 0, the result is 0. Therefore, third option is also true. Third option is also true, which is equal to 0 is also true. Now, what about fourth option? When you look at fourth option, del square v by del x del y plus del square v by del y del x. Del square v by del x del y plus del square v by del y del x. Del by del x of del v by del y, del by del y of del v by del x. Vy equal to minus ux. Ux equal to vy. Vy equal to ux plus del by del y of Vx equal to minus uy. By substituting this, we got del square u by del x square minus del square u by del y square, which is not 0. So non-zero. In the statement, they have provided equal to 0. This is false. So first option is correct, second option is correct, third option is correct. MSQ with 3 options A, B, C are correct. Next column, z minus 1 by e power 2 pi I by z minus 1. Then the function has which type of singularity? We have to identify. So the function of z is f of z is z minus 1 by e power 2 pi I by z minus 1. 2 pi I by z minus 1. Now we have to find out singularities. To find out singularities, I am going to equate denominator of the function to 0. Here the singular points are e power 2 pi I by z minus 1 equal to 0. E power 2 pi I by z equal to 1. Now this 1 can be written as e power 2 I pi. E power 2, 1 minute. 1 is nothing but e power I 2n pi, where n belongs to z. Now, so n belongs to z means n is 0, 1, 2, 3 and so on, minus 1, minus 2 and 3 and 3, minus 3 and so on. So here n is an integer. Now e power 2 pi I by z equal to e power I 2n pi. Therefore, when bases are equal, automatically powers are equal. Therefore, 2 pi I by z equal to I 2n pi. That's why I am going to equate 2 pi I by z to I 2n pi. From this, I 2 pi cancel, 1 by z equal to n. 1 by z equal to n. That means z equal to 1 by n belongs to z. That means here the singular points are n equal to 1, n equal to 2, n equal to 3. Like that, infinite number of singular points here we have. Infinite number of singular points we have. Okay. Now, which type of singularity we have to identify? Observe option A. He has given isolated singularity at z equal to 0. This is incorrect. Here z equal to 0 is not an isolated singularity because z is 1 by n. If you put n equal to 0, it is 1 by 0 form. So it is not an isolated singularity. So eliminate that. First option is incorrect. Now coming to second option. The function has removable singularity at z equal to 1. Whether it has removable singularity or not, we are going to cross check. How to cross check? Just examining limit z tends to 1. Observe. Limit z tends to 1. Z minus 1 into function of z. We are verifying option B. Now, z minus 1 into function of z. Our function of z is z minus 1 by e power I 2 pi by z minus 1. If you look at the limit, you can understand that clearly L'Hospital rule is applicable. When z is tending to 1, in denominator 1 minus 1, 0, 0 by 0 form. 0 by 0 form comes, we have to apply L'Hospital rule. So limit z tends to 1. Differentiation of denominator e power I 2 pi by z into differentiation of I 2 pi by z. I 2 pi by z. Here I into 2 pi by z. Right. Now, numerator 2 into z minus 1. When z is tending to 1, which is 0. Which is 0. Therefore, the function has a removable singularity. Therefore, the function has a removable singularity. The function has a removable singularity. Therefore, second option is true. Next, f has many number of poles. Yes, that is also true. Infinite number of poles is true. Next, each pole of f is of order 1. That is also true. Because you have infinite number of poles, if you put z equal to 1, you will get 1 pole. When n is 2, z equal to 1 by 2, 1 pole. Z equal to 1 by 3, 1 pole. Like that you have infinite number of poles. Every pole is a simple pole. That's why last option is also correct. So B, C, D are found correct in this problem. 3 options are correct. Next, the function e power z by e power z minus 1. The function is entire, first option. Only singularities of f are poles. F has infinite number of poles on imaginary axis. Each pole of f is simple. Similar type of problem. E power z by e power z minus 1. Function of z is e power z by e power z minus 1. The singularities are e power z minus 1 equal to 0. e power z equal to 1. 1 can be written as e power I 2n pi. Therefore, z equal to I into 2n pi, where n belongs to integer. Z plus z, z means here this z is complex number, this z is complex number, this z is integer. Okay, set of integers. Now here for different values of n, are you going to get different number of poles or not? Therefore infinite number of many poles on imaginary axis is true. The only singularities of f are poles. This is also true. We got the singularities. Z equal to I 2n pi. Z equal to I 2n pi. You have infinite number of singularities. Therefore, the only singularities are poles. So, second option is correct. Third option is correct. Each pole of f is simple. So, last option is also correct. All are simple poles. Infinite number of simple poles for your function. The function has a pole means it is not entire. So, first option is incorrect. Entire means analytic everywhere. If the function is analytic everywhere, on the complex plane, then that function has no singular points. But here you are getting infinite number of many singular points on imaginary axis for the given function. Therefore, it is not entire. So, first option is incorrect. Remaining three options are found correct. B, C, D, MSQ, all B, C, D are found correct. Three options are correct. Sagar, good evening. Arshad. Now, next problem. The function is halomorphic. Halomorphic is nothing but analytic. Halomorphic or analytic, both are same. Now, let u be the real part of f of z and v be the imaginary part of f of z. Then f dash of x plus iy whole square. F dash of x plus iy whole square means mod f dash z whole square. Mod f dash z whole square. We have to find out. Now, what is f dash z? F dash z is nothing but ux plus ivx. Mod f dash z is nothing but square root of ux square plus vx square. Mod f dash z whole square is nothing but ux square plus vx square. This is called equation 1. Now, we have to examine option wise. First option. Option A. Option A is ux square plus uy square. Now, from equation 1, f dash z whole square is ux square plus vx square. Ux square plus vx square. Observe, this is true. Second option is straight away true from equation 1. Now I am examining first option. What is first option? Ux square plus uy square. Now option A is ux square plus uy square. Ux square plus uy square. From equation 1 we got from equation 1 we got mod f dash z whole square is ux square plus vx square. So in the place of vx you can write minus uy. Ux square is ux square, no change. Ux square minus uy whole square is uy square now. Therefore, this is true. Second option is already true. I have written clearly. Now this is also true. Now third option. We have to check third option. What is third option? Third and fourth I am examining. Third option is Vy square. Third option is Vy square plus Uy square. Third option is Vy square plus Uy square. Observe. F dash z mod f dash z whole square is ux square plus vx square. In the place of ux, if you write vy, then vy whole square. In the place of vx, if you write minus uy whole square, that is vy square plus uy square. This is also true. Third option is true. Now verify fourth option. What is fourth option? Vx square plus vy square. Mod f dash z whole square is ux square plus vx square. Now in the place of ux, if you write vy whole square plus vx whole square, na? Therefore this is also true. Last option is also true. So all four options are correct in this problem. All four options are correct. Next problem. E power z by z power 2018 be a complex function. Then the function has simple pole or pole of some order or residue. We have to calculate. Now let us take the function f of z is e power z by z power 2018. E power z by z power 2018. Now this can be written as 1 plus z by 1 factorial, z square by 2 factorial, and so on. Z power 2017 by 2017 factorial plus z power 2018 by 2019 factorial, and so on, divided by z power 2018. After simplification, this will become 1 by z power 2018 plus 1 by 1 factorial into z power 2017, 1 by 2 factorial into z power 2016, and so on. Now z power 2017 by 2017 factorial divided by z power 2018 means 1 by 2017 factorial into z plus 1 by 2018 factorial, and so on, like that. So you have how many negative powers of z? Only finite number of negative powers of z. These are all negative powers of z. From here onwards, your positive term series starts. Here 1 by 2018 factorial plus z by 2019 factorial, and so on. That's why only finite number of negative powers of z. If you have finite number of negative powers of z, compulsory it is a pole. So here finite number of terms in the principal part, finite number of negative powers of Z. Therefore, it is a pole. Therefore, Z equal to 0 is a pole. Pole of which order? Actually here numerators are not 1. This series is there. This series is there. This series is there. Okay. That series divided by Z power 2018. So 1 by 2000 Z power 2018. So here Z by Z power 2018 is 1 by 1 factorial into Z power 2017. Z square by 2 factorial into Z power 2018 is Z power 2016. Like that I have written. So infinite finite number of negative powers of Z. Therefore it is a pole. Therefore Z equal to 0 is a pole of which order? Of order in negative powers of Z. Which one is maximum? Z power 2018. Z power 2018. 1 by Z power 2018. This decides pole of which order? Pole of order 2018. So Z equal to 0 is a pole of order 2018. Next, residue. Residue of f of Z at Z equal to 0 is coefficient of 1 by Z in the series expansion. In this series, you have coefficient of 1 by Z is available here. Observe this term, this term. This term decides coefficient of 1 by Z. 1 by 2017 factorial. 1 by 2017 factorial. Okay. So 1 by 2017 factorial is the residue. This is true. F of Z has a simple pole at, it is not a simple pole. This is false. F of Z has a pole of order 2018. It is true. Residue of f of Z at Z equal to 0 is 1 by 2018 factorial is false. So which one is correct? Second option and third option. B and C are found correct. Next problem. The function f of Z is analytic at Z equal to Z0. Then the function is continuous at Z equal to Z0. True. F is differentiable at Z equal to Z0. True. The function is differentiable at each point of some neighborhood of Z equal to Z0. True. All of the above. That is also true. So 4 statements are correct. A, B, C, D. Next problem. The function f of Z equal to u plus iv is analytic. U of xy is cos x cos hy. Then v of xy we have to find out. U of xy is provided. We have to find out v of xy. First option, u is harmonic. U is a harmonic function. Second option, u is not harmonic. Third option, v of xy is cos x sin hy. Fourth option, v of xy is minus sin x sin hy. Now, in this problem, if the function is analytic, clearly, u is harmonic. V is also harmonic, therefore first statement is true. Second statement, second option, U is not harmonic, it is false. Second option is false. Now third or fourth we have to decide V. Now U is provided. U is equal to cos x cos hy. Therefore Ux, differentiating U partially with respect to x, we will get minus sin x cos hy. Now Ux is known. If the function is analytic, definitely CR equations are satisfied. So in this problem, the given function is analytic. Therefore compulsory Ux equal to Vy. Compulsory Ux equal to Vy. Now in third option he has given V is cos x sin hy. Cos x sin hy. In fourth option he has given V is minus sin x sin hy. Now we know that in the previous slide we have calculated Ux equal to minus sin x cos hy. Compulsory Ux is equal to Vy. By CR equations, Ux equal to Vy. Now I would like to find out Vy by using option C and option D. Now differentiate V with respect to y. Cos x is constant because you are differentiating with respect to y partially. Differentiation of sine hyperbolic is cos hy. Now here I am differentiating V with respect to y. Minus sin x. Differentiation of sin hy is cos hy. That is minus sin x cos hy. When you compare with Ux is minus sin x cos hy. Vy is also minus sin x cos hy in option D. That's why third option is false, fourth option is true. So third option is false, fourth option is true. Because CR equations are satisfied by last option. Therefore both A and D are found correct. Now next problem. If R1, R2, R3 be residues of f of z at z equal to 0, 1, 2, then which of the following statements is are true? We have to find out. Which of the following statements are true? Now the function f of z is 2 by z into z minus 1 into z minus 2. 2 by z into z minus 1 into z minus 2. So z equal to 0 is simple pole, z equal to 1 is simple pole, z equal to is also simple pole. Now we have to calculate residues at 0, 1, 2. Now R1 is nothing but residue of f of z at z equal to 0. That implies limit z tends to 0, z into 2 by z into z minus 1 into z minus 2. Here z and z cancel. 2 by 0 minus 1 into 0 minus 2. 2 by 2, 1. R1 is 1. R2 we have to calculate. Now R2 is residue of f of z at z equal to 1. Limit z tends to 1, z minus 1 into function of z, 2 by z minus 1 into z minus 2. Z minus 1 cancel. When z is tending to 1, you will get 2 by 1 minus 2, that is minus 2. Residue is minus 2. R2 is minus 2. Next, R3. Residue of f of z at z equal to 2, that is limit z tends to 2, z minus 2 into function of z, 2 by z into z minus 1 into z minus 2. Z minus 2 cancel. That is, when z is tending to 2, 2 by 2 into 2 minus 1, that is 1. Now R1 is 1, R2 is minus 2, R1 is 1, R2 is minus 2, R3 is 1. Now we have to verify R1 plus R2 plus R3. Here itself I would like to verify. We got R1 is 1, R2 is minus 2, R3 is 1. Substitute here. In first statement, R1 plus R2 plus R3, 1 minus 2 plus 1 equal to 0. That is true. Next, second statement, second option. 4R1 4 minus R2, minus of minus 2 is plus 2, minus 6R3 minus 6, 6 minus 6 0. That statement is true. Now third option, R1 1, 3R2 minus 6, 5R3 plus 5, that is also 0. So this is also true. Last statement, last option, 4R1 4 plus R2 minus 2 minus 2R3 minus 2, 4 minus 4 0. This is also true. So all four options are found correct. All, yeah, by substituting R1, R2, R3 in, by substituting in option, in the options, in the given options, we got all four options are found correct. Next problem, f of z equal to mod z square, f of z equal to mod z square, then the Cauchy-Riemann equations are satisfied only at z equal to 0. The Cauchy-Riemann equations are satisfied for all z. The Cauchy-Riemann equations are not satisfied at any value of z. The function is not analytic at z equal to 0. We have to verify. Mainly the function f of z equal to mod z square. Now the function f of z equal to mod z whole square. F of z is nothing but u plus iv. Mod z is nothing but square root of x plus, mod z is nothing but square root of x square plus y square. Mod z whole square is square root of x square plus y square whole square. Therefore x square plus y square. Now, if you compare real part and imaginary parts, real part u is x square plus y square, imaginary part v is 0. Now ux is 2x, uy 2y, vx 0, vy 0. CR equations are not satisfied in general. In general, CR equations are not satisfied. Okay, but ux, uy, vx, vy are continuous because polynomials, constant functions, ux, uy, vx, vy are continuous for all z. Okay, ux, uy, vx, vy are continuous for all z, but CR equations are not satisfied right now. Now, if you take z equal to 0, at z equal to 0, because in the options he has provided at z equal to 0. Z equal to 0 means x equal to 0, y equal to 0. When x is 0, y is 0, now ux is 2x na 0, uy 2y, that is 0, vx 0, vy 0. At z equal to 0, CR equations are satisfied. At z equal to 0, CR equations are satisfied. You can write in another way, ux equal to vy, ux equal to vy and uy equal to minus vx. CR equations are satisfied only at z equal to 0, but not in its neighborhood. CR equations are satisfied only at z equal to 0, but not in its neighborhood. Therefore, the function f of z equal to mod z whole square is differentiable at z equal to 0. Differentiable at z equal to 0, but not analytic at z equal to 0. It is differentiable at z equal to 0, but not analytic at z equal to 0. Therefore, in the given options, the function is not analytic at z equal to 0. That is true. Last option is true. CR equations are not satisfied at any value of z. That is false, because CR equations are satisfied at z equal to 0. That's why third option is false. Now, when you come to second options, CR equations are satisfied for all z. No, it is false, because you have verified already here ux equal to 2x, vy equal to 0. 2x equal to 0 is not possible for all values of z. That's why CR equations are satisfied for all values of z is false. But first option is true, because Cauchy-Riemann equations are satisfied only at z equal to 0 is true. Only at z equal to 0 is true. Therefore, first option is correct. Last option is also correct. Second option and third option are incorrect. Second option is incorrect because he has mentioned CR equations are satisfied for all z. So it is incorrect. It is CR equations are satisfied only at z equal to 0. Not satisfied at any value of z. That is also incorrect, because we are giving one counter example at z equal to 0 CR equations are satisfied. That's why first option and last option are found correct in this problem. Unacademy is introducing new subscription plan for GATE and ESE, 18 months subscription. Use in plus subscription you have DPPs, weekly monthly tests, doubts clearing sessions, live and interactive lectures, unlimited access by one subscription. Use code KUR75 to get either plus subscription or iconic subscription. Thank you.